Okay, Level 3 2024 Mechanics Past Paper. Fun fact, this was actually my exam that I took when I was year 13. Yes, in fact, I am not that old. I know for a fact some of you thought I was like 21 or something. So this should be pretty good. And yes, if you're wondering, I did get excellence. We're good. Okay, so we're asked to calculate the angular velocity at this point right here. Okay. Now we know directly from our formula sheet that v is equal to r omega, and therefore angular velocity, which is omega, is equal to omega v over r. So we are given the velocity up here, and our radius is not this value right here. It is this value, 7 millimeters. The reason why it's 7 millimeters is when we are converting from linear velocity to angular velocity, which is what this equation is doing, we are interested in the radius of the object, not the radius of the thing it's going around, okay? And so we can plug in those numbers, 0.85 all over 7 times 10 to the negative 3, right? The reason why it's times 10 to the negative 3 is because this is in millimeters, and in our formula, the radius is in meters, so we need to convert it back to meters. And this gives a value of 121.43 radians per second. There we go. Show that the maximum speed is 0.586 meters per second in order for the ball bearing to remain in contact with the track while going over the bump at point Y with the radius of 35 millimeters. So that is point Y right over here. So this question is essentially just a vertical circles question. So if you haven't watched my video on vertical circles, I think it's pretty good, so you can check it out. But this time, rather than asking for a minimum speed, we're asked for a maximum speed. So that could throw some people off. I'm pretty sure it did when I was doing the exam. But essentially, it's asking the same thing as minimum speed, just in a different scenario. I'll explain. So first, when we have our minimum speed scenario, we have a circle of some kind, right? This could be like a roller coaster, let's say, all right? And we have our ball at the top. When we are talking about minimum speed, the entire centripetal force is provided entirely by the weight force. So that means that the normal force that would have been provided by the track is equal to 0 newtons, right? And so we get Fc is equal to Fw. Now this is minimum speed because if we were going any slower, we would not make contact with the track and just fall straight down like this, okay? So the minimum speed is the minimum velocity that we need in order to keep going along the loop. This is very, very similar for this question. In this question, we have a situation where we have like a hump like this, right? And we have our ball going like this, and we want to find what's the maximum velocity that we can have the ball travel along the hump, essentially. We can imagine if we go too fast, we're going to go straight off the hump and catch airtime. So we don't want that. We want the maximum speed to remain in contact with the track, okay? So now if we analyze the forces in this scenario, we have a normal force and we also have a weight force, right? And we can imagine that this hump is part of a bigger circle. And now you can see that in this scenario, rather than being on the inside of the circle, we are on the outside of the circle. And so if you remember, the Fc is the net force that acts towards the center of the circle. And so in this case, the net force that acts towards the center of the circle is the weight force minus the normal force, right? Weight force minus normal force will give us the net force that's acting downwards, okay? Now, just like in the minimum speed example, we reach minimum speed when the normal force is equal to 0. So the ball is barely touching the track. Like, it's still touching it, but it's not touching enough for the track to provide a normal force. And remember how I said if the velocity was any less, we would fall straight down. In this scenario, it's the same thing, just in reverse. Like I said before, if we have too much speed, we go straight off. So we want to know what's the maximum speed that we can obtain for the ball such that the normal force is equal to 0 and the ball is just touching the track as it goes over. So the normal force is 0 in this scenario. And so because it's 0, we can cross that out and we get Fc is equal to Fw. And then from there, it's just our simple mg is equal to mv squared over r. These m's cancel out, and we get g is equal to v squared over r. Gr is equal to v squared, and therefore square root gr is equal to v. Now, plugging in our numbers, we obviously know that g is 9.81, and our radius is 35 times 10 to the negative 3, again converting to meters from millimeters. And this gives us a velocity of 0.586 meters per second. And I believe that is the value that we are trying to find right there. Alright, so this question is our classic excellence question where we compare the forces at like 2 points in a vertical circle. Again, this is pretty much a vertical circle scenario with some slight differences like I explained in the previous question. So we can go through them. Let's start off with point X, okay? At point X, we can draw our simplified diagram like this. This is point X. We have a normal force being provided by the track and obviously a weight force going straight downwards. Now, as you can see, this is our regular vertical circle scenario at the bottom of the track. And so therefore, as FC is the net force towards the center of the circle, our FC is equal to our normal force minus our weight force. And therefore, our normal force is equal to our FC plus our weight force. And therefore, our normal force at point X is largest. At point Y, we had the scenario that we had in the previous question where we have our ball on top of a hill. Our weight force is directly downwards and our normal force is upwards again. So in this case, again, since the centripetal force is the net force towards the center of the circle, our FC is equal to our weight force minus our net force. Now, in order to make these diagrams more accurate, I should probably A, make this normal force larger than the weight force, because as the normal force is both countering the weight force and providing the FC, it needs to be larger. And in this scenario, the weight force needs to be larger than the normal force, because this scenario is the opposite of this scenario, right? So our weight force is the force providing the FC, right? Now, also, minor detail, I don't know if they're going to pick up on this or not, but your weight force arrows should be roughly the same size, because in this scenario, I made the normal force larger, but in this scenario, I decided to make the normal force smaller. If you were to make the weight force larger, that would be incorrect, because the weight force of the ball does not change, because the mass of the ball does not change, and obviously gravity isn't going to change. So for these diagrams, for point X, you must make the normal force larger for point X, and for point Y, you must make the normal force smaller. And also, just like always, you can't just write this and get excellence, you also need words as well. So you can write that in based on the theory. All right, so we have a classic conservation of energy question here. So if we bring back our diagram, we are trying to find this height right here, okay? So based on energy conservation, we should know that the gravitational potential energy at this point right here should be equal to the linear kinetic energy, right, plus the rotational kinetic energy at this point right here. Now, the reason why I'm using this point and not this point is purely because this distance right here is equal to h, right, at point Y. If I were to use point X, I would also have to consider this 35 millimeters, and it just makes our calculation slightly harder. I haven't done the calculation myself, but you should get the same answer, but also you shouldn't just make your life harder, so I'd highly recommend just using point Y. So based on what I set up here, our mgh is equal to our half mv squared plus our half I omega squared. Now we're given our value for I, so we can make that substitution. And we also know that omega is equal to v over r, so we can make that substitution as well. And we get mgh is equal to half mv squared plus half 2 over 5 mr squared v over r squared. So now just carrying on the calculation, we got mgh is equal to half mv squared plus 1 over 5, right? 1 half plus 2 over 5 is equal to 1 over 5 mr squared times v squared all over r squared. Now, as you can see, this r squared and this r squared gets cancelled out, and we got mgh is equal to half mv squared plus 1 over 5 mv squared. Now we can divide by m on both sides as well, and you can cancel out these m's, and we get gh is equal to half v squared plus 1 over 5 v squared. Now we got v squared as a common factor, So half plus 1 over 5 is equal to 7 over 10. So we get 7 over 10 v squared is equal to gh. And therefore our h is equal to 7 over 10 times v squared all over our g. So now what is our velocity? Well, because we picked point y, we can just go back up here and use the given value that is given to us of 0.586, right? So our height is equal to 7 over 10 times 0.586 squared all over 9.81. And therefore our height is equal to 0.0245 meters. There we go. Now, in the marking schedule, if you have looked at it, you will see that there is method A and method B. I have looked at it, and from what I can tell, method A and method B are the exact same thing. The only difference is that the order in which you do things is different. In method A, they calculate omega first, and then they use that to calculate their EK rot, and then they calculate their EK linear, and then they combine that to make it equal to the gravitational potential energy rearranged for H. So it's basically what we did, just the order is different, right? Sweet. Okay, so a golf ball is placed into a light cup and is attached to a flywheel, begins to accelerate downwards at a constant rate of 1.83 meters per second. Show the angular acceleration of the flywheel is 16.6 radians per second. Okay, just a light one to start us off. We know that our acceleration is equal to r alpha, right, where our alpha is our angular acceleration. And therefore we can rearrange for alpha, so our alpha is equal to a over r, right? Then subbing in our numbers, 1.83 all over our radius, which is not 0.220, it is 0.110, because this is the diameter, not the radius, don't get that mixed up. And this gives us 16.64 radians per second, which is the value that we're trying to find. If the ball and cup start from rest and fall through a distance of 0.75 meters, calculate the final angular velocity of the flywheel. So the equation that we'll be using is the final angular velocity squared is equal to the angular velocity initially squared plus 2 alpha beta. Now we are given the initial angular velocity because it says it starts at rest, so omega I is equal to 0. So we can just cancel that out. And we can say omega f squared is equal to 2 alpha theta. We just calculated the angular acceleration up here as 16.64, so we know that. And we are trying to find the final angular velocity, which is this. So the only thing that we don't know is our theta. Now theta, if we imagine our flywheel, and we have our cup here, right? Our cup, and this is attached by a rope. If our cup travels, let's see, this distance right here is 0.75 meters. So it's gone down by 0.75 meters, which is what it says up here. We can imagine that the flywheel is going to rotate a certain distance. Now, this distance we can think of as an angle. It's going to rotate through a certain angle. So that angle might be like this much, theta, right? And so what is that angle? Now, luckily we have an equation for that. We have our distance is equal to r theta, right? So basically what this equation tells us is the angle that the flywheel has rotated given a certain distance that it's being pulled downwards, right, by the cup. And so we can rearrange for our theta and we get d over r. And so therefore our theta is equal to 0.75 all over the radius of the flywheel, which I'm pretty sure is given. Oh yes, I pointed it out. It's 0.110. And therefore our theta is 6.8 radians. That's pretty big. Remember, our full rotation is 2 pi, and 2 pi is 6.2 something, 6.28, right? And so that's more than one full rotation. So this diagram is wildly inaccurate. But anyways, we can sub in our numbers, and we can say our final angular velocity is equal to the square root of 2 alpha theta, and therefore our final angular velocity is equal to square root 2 times 16.64 times 6.8, running out of space, and therefore our final angular velocity is equal to 15.1 radians per second. There we go. Now, I did use 16.64 for this calculation. I highly recommend that when you put it in your calculator, you use full values so you get the absolute correct answer. Bit of a hypocrite because I didn't do that just now, but I'm also not taking the exam right now, so... But yes, please, do use full values. You don't have to write the full value when you're doing your working. You can write this, like a shorthand rounded version on your paper, but in the exam, in your calculator, put the full value. Okay, calculate the rotational inertia of the flywheel. Begin your answer by calculating the force that's causing the flywheel to accelerate. Okay, use the free body diagram. Now, before we calculate the force that's causing the flywheel to move, what is the force that's causing the flywheel to move? Well, we can use that using free body diagrams. So let's draw our flywheel, right? And we know that there is a rope coming down here that's connected to a cup. But we can simplify that as a force. So there's a force coming down this way, okay? This force, if we can imagine, is the force that's causing the flywheel to rotate. Now, what is that force? Well, we can draw another free body diagram of the cup, right? There we go, cup. Let's draw an internal wall. There we go, cup. So we know this cup has a weight force coming straight down, and because it is attached to a rope, there is a tension force coming back up this way. Tension force, there we go. Now, a common mistake that I can foresee people making is that they will go, weight force is equal to tension force, and then solve for tension force, being like mg is equal to ft, and then plugging in the mass of the cup. That is wrong. The reason for that is because you are used to everything being in equilibrium, everything being at rest. In this scenario, it is not at rest. It is accelerating at a constant rate of 1.83 meters per second. So what that essentially means is the forces are not balanced, because in order for it to be accelerating at a constant rate, the forces must be unbalanced, and therefore there is a net force. Now, if we put a coordinate system and take down to be positive, right? We can say our net force is equal to our weight force minus our tension force, right? Because positive is down, so therefore this is positive, and this will be negative, so therefore we minus. Now, what is our net force? Well, we know F is equal to ma, and so therefore our mass times our A, we can call that A net, so our net acceleration is equal to our mg minus our ft, which is also equal to ma, right? And now this A is equal to this A right here. And so we can also cancel out our masses on both sides, and we get our net acceleration is equal to g minus our acceleration, and therefore 9.81 minus 1.83 is equal to our net acceleration. This gives a net acceleration of 7.98 meters per second. Now, the force in and of itself is not what causes the flywheel to rotate, because it is actually the torque applied by the force, because torque is a rotational force, right? And so we know our torque is equal to our force times our distance, and this force right here is our net force, which we can calculate as F net is equal to our m times our net acceleration, where our mass is 0.0460, right? That is given up here, times our net acceleration, 7.98, and that gives us a net force of 0.36708 newtons. There we go. And this distance right here is the distance between where the force was applied and the axis of rotation. Now, the axis of rotation in this case is the center of the flywheel, and the force is applied on the outside of the flywheel, right? Just like right on this edge. And so this distance is the radius of the flywheel, which we have seen a bunch of times, is 0.110, which is 0.110 meters, right? And therefore we can calculate our torque is equal to 0.36708 times our distance of 0.110, and this gives us a torque of 0.040378 Newton meters. There we go. Now we also know that our torque is equal to our I alpha. Now our I is what we're trying to find, and so we can rearrange that, and we get our torque all over our alpha. Our alpha we found up top, which is 16.6 radians per second, right? That's an S, don't worry about it. And so we can just plug in our numbers, 0.040378 all over 16.6. This gives us a rotational inertia of 2.43 times 10 to the negative 3 kg meters squared. There we go. Explain what will happen to the final velocity of the ball and cup if the flywheel is replaced with a solid disc with the same radius and mass. We know our rotational inertia is directly proportional to our mr squared. The reason why I'm not saying equals in this case is because there are cases, as we've seen in this exam, where we have 2/5 mr squared, oh, mr squared, or 1 over 2 mr squared, right? It's not always equal to mr squared. It's equal to mr squared when all the mass is on the outer edge of the circle, which in this case, we know it's a solid disk, and we know that's not the case, right? So directly proportional. So our mass stays the same, so we don't need to worry about that. Because the distribution of mass has now changed, the effective radius has decreased. Now, what is effective radius? Sounds like a fancy term. What does it mean? Blah, blah. I'll explain it in slightly simple terms, okay? If we take the rotational inertia of a ring, right? So a ring is where we have all the mass on the outer edge. That is equal to mr squared, right? We're going to use big R for the radius, okay? However, if we have a disk scenario, we know that's equal to half mr squared, right? And so because we know that I is equal to mr squared, we can rearrange this for square root I over m. And so if we want to calculate the effective radius, we can go R effective, right, is equal to square root I over m. Now, if we substitute the rotational inertia of the disk into here, we get square root half times mr squared all over our m. Now, this m can cancel out, and we get square root half r squared. And therefore, our effective radius is equal to square root half times r. Square root 1 over 2 is equal to 0.707 times our r. So as you can see, our effective radius is only a fraction of our full radius, right? We said before our full radius is big R, and so our effective radius is only 0.07 of the original radius when the radius was just a ring. Now, don't worry if you didn't follow that derivation like fully. First of all, it wasn't a very robust derivation, and secondly, it's not required for level 3, so if you don't have that knowledge, don't worry for the exam. But what I hope you got out of that was that now you can recognize that the effective radius, when we say that, we're basically saying it's equivalent to a fraction of the original radius when we take the radius of a ring. Okay, so that was kind of a side tangent, but what we know is that when the flywheel turns into a disk, the effective radius has now decreased. Okay, so now because the effective radius has decreased, our rotational inertia has decreased. Now, as torque is equal to I alpha, if our I has now decreased, but the torque applied to the disk has remained the same, therefore our angular acceleration must increase. And also because A is equal to R alpha, therefore, as our radius of our disk has remained the same, now our effective radius in terms of rotational inertia has decreased, but the actual radius of the disk is the same as the flywheel. And that's what this is talking about, the actual radius, okay? So because our actual radius has remained the same, if our rotational acceleration has increased, therefore our linear acceleration must increase. And because acceleration is velocity all over time, if our linear acceleration increases, therefore our velocity must increase. And so therefore you can explain that in words. Again, you don't need to explain this in your answer. You can just say that the effective radius has decreased and you'll still get the mark because you're not expected to know this knowledge in level 3. A ball bearing is released on a watch glass and rolls back and forth in simple harmonic motion. Alright, state the 2 conditions necessary for the ball bearing to be considered to be moving in simple harmonic motion. The restoring force must be proportional and in opposite direction to the displacement. The ball bearing is released 0.04 meters from the right of the equilibrium position and oscillates with a time period of 0.882 seconds. Use the reference circle or otherwise to calculate the displacement of the ball bearing after 1.2 seconds. Okay, so if you have not watched my recent video on reference circles, highly recommend it. But if you have, cool. Sweet. Let's draw this reference circle much bigger because that is tiny. Like that. So it says over here, we're released 0.04 meters to the right of the equilibrium position. So like we can say that's right here. Yeah. And we can trace that down. So we're starting here on the reference circle. Now, 0.04 meters, therefore, is our amplitude. We have a time period of 0.882 seconds, and we're trying to find the displacement of the ball bearing 1.2 seconds after. So therefore, we know it's going to complete 1 full rotation and then some after we take the calculation. So it's probably going to start from here, come around, back here, and end up probably around this point right here. So let's put that, there we go. Now, it says the displacement. So displacement is not total distance, okay? If we have Timmy over here, and Timmy wants to go to his house, okay, and his house is 5 meters away. If Timmy travels to his house and back, he has traveled a total distance of 10 meters, but his displacement is 0 meters, right? So displacement is the total distance you have traveled, so displacement has direction. So we're trying to find the displacement from the starting point, so that is actually this distance right here, right? This distance, okay? So that is the D that we're trying to find, this line right here, okay? And we can trace that down if we want, right? So that is, again, our distance, okay? So we can draw our phasor in like so. So we know that our theta is equal to omega t, and we also know that our omega is equal to 2 pi all over our period. And so our theta is equal to 2 pi all over t times our time. So therefore our theta is equal to 2 pi all over our period of 0.882 times 1.2 seconds, and therefore our theta is equal to 8.55 radians. There we go. Now, because we have started from max displacement, our x of t is going to be a cos theta, right? And so our displacement at time 1.2 seconds is equal to 0.04. That's our amplitude, cos 8.55, and therefore this gives us a displacement of negative 0.0256 meters. There we go. And again, the negative, because we're talking about displacement, is basically saying it just moved this way rather than this way, okay? Which we can see it has. So, all good. Eventually, the ball bearing comes to rest. Use the axes provided to draw a labeled graph of the displacement versus time of 5 complete oscillations. Include the values for displacement and time. Okay, so this is our period axis, and we have 1, 2, 3, 4, 5. Okay, so that's 1t, 2t, 3t, 4t, 5t, right? And our max displacement was 0.04, and therefore our max displacement in the opposite direction is 0.04 also, but negative, obviously. And the idea here is that we want to decrease the amplitude in even amounts after each time. So what we want to do is we want to come down to, let's say here, and go like this, come up to here. So what you should notice is that we decrease the amplitude by 1 square on this side, right? And then on this side, we decreased it by 2 squares. So every time we go down, we decrease it by 1, and then we go up, we decrease it by 2 because we've done it twice now, okay? You don't always have to decrease it by 1 square. You just need to be consistent, okay? So don't go 2 squares here and then you only do 1 square here. 1 each time, or 2 each time, or 3 each time. Don't recommend you doing 3. There's usually not that many squares, but you get the idea. And so we can do that again, where we go like this now, and we come down there, go here, come up, and there we go like here, come down again, there, come down to here, and it's like this, and then we're good. We go like that. There we go. And in the end, your graph should make this shape like that, like it should go. So did pretty good. Name this phenomenon and explain in detail why the ball bearing eventually comes to rest. Answer with relevant formulae. So as the ball bearing is oscillating, I'm pretty sure it's a situation like this, where we have our ball bearing moving from side to side like this, okay? As you can see, at this point, it has max potential energy, gravitational potential energy, and if it's at max displacement, then it's also momentarily at rest, and therefore, as our EK is equal to half mv squared, if our v is equal to 0, our EK is also equal to 0, right? So it has max gravitational potential energy and minimum kinetic energy, right? And then as it comes down, it converts that gravitational potential energy into kinetic energy. And at this point, it has the least gravitational potential energy and the most EK. And then it comes up here and the cycle repeats. However, because this is real life, this process is not 100% efficient. We lose energy to things like friction. And so therefore, as the ball comes down, not all the gravitational potential energy is converted into EK. And therefore, same thing, not all this EK is converted into gravitational potential energy. And so the gravitational potential energy at this point is going to be less than the gravitational potential energy at this point. And this will keep happening And therefore, the amplitude will slowly decrease, which you can see over here. Amplitude slowly decreasing, okay? And it said use relevant equations, that the equation is just the energy total is equal to EK plus UP. And also this phenomenon is called damping. I don't know if I said that earlier, just putting it out there, okay? Sweet. And yeah, you can write an answer based on that theory. And with that, we are done. Sweet as.